So, okay. Good morning. So, welcome to the exam 3 review for Math 16010. So, so just a couple quick announcements before we get started. Exam 3 is, well, of course, starts tomorrow at 9 a.m. and you have until Friday to complete it. Covers lessons 19 through 28. And because of the exam, there will be no class this Wednesday, but there will be class this Friday. So this Friday we'll be starting the final units of new content. And then extra credit 4 will be due Tuesday, well, basically tomorrow at 9 a.m. And keep in mind, the extra credit 4 was sent via email, so please make sure to check that from last week. And one thing to keep in mind is that I will be, again, strict about this deadline. Meaning if I see something at 9:01 a.m. on Tuesday, it's not going to get accepted. So just keep that in mind when you're doing the extra credit. Okay? So, other than that, so that you guys have had plenty of time to look at some exam style problems and such for the exam. What questions do you guys have? Anything that comes to mind?
Yeah, could you go over an optimization problem where it's the window with the semicircle on top of the rectangle?
That's going to be fairly long, so I'm actually not going to cover that. But the thing is that actually the answer to that is on the webpage.
Okay.
So I think so let's go back to that for a second. So let me pull that up. 6010. So, oops. That's the wrong lesson. I'm looking for lesson 25. So, we're talking about this guy right here?
Yeah.
Okay. So the thing is that if you actually look at this, the algebra for this is relatively long and it's not super quick.
Mm-hmm.
So the thing is that to sort of save time, what I ended up doing for this was I kind of just said, if you have a parameter p, here's the desired dimensions you're looking for.
Okay.
So, because of that, I would not expect a question like that to show up on the exam.
Okay.
Because that is fairly long in terms of the calculations. So, okay. Any others that stuck out to you guys? Any questions you all want to take a peek at?
What lessons are in this exam?
19 to 20.
Okay, thank you.
Okay. Any others that stuck out? Give you guys a second to look at some of the notes, see if anything looked a bit concerning.
Can you go with like the end of the derivatives where you find C?
Yeah, we can do that.
And some limits on infinity.
Sure. Okay. So let's do that. So let's start off with those. Does anyone have any other ones they want to look at before we move to those? Okay. So let's do this. So let me go back to this. So let's do an example of this. Let's start off with the antiderivative stuff. So we have to solve this IVP where we have y prime equals 1 plus 10x e to the x over x. And then we're given y1 equals 12. Okay? So basically, if you recall from last time, what IVP tells you is that we have some function whose derivative, or in some cases second derivative, is given as this expression here. But in addition, we're also given some data points. So what this means is that this allows us to find the general antiderivative, but this extra condition here allows us to actually figure out what the value, the arbitrary constant c is. Okay? So let's take a look at this. So if we have y prime equals 1 plus 10x e to the x over x, well, if you probably could figure out that at this point, if you want to figure out the antiderivative of this, well, you got to take the integral, right? So we have y of x equals the integral of 1 plus 10x e to the x over x dx. But then you realize, well, wait a minute, how do I take the integral of this? There's not really any actual integral rules that actually allows us to work with this explicit expression. So how do we fix that? Yeah, we got to split it up, right? So we have, in this case, we have 1 over x plus 10x e to the x, divided by x dx. So splitting this off as, will give you this. Okay? So in terms of what we have, there's not really much we can do with the first term in terms of further simplification, but what about the second term?
You can cancel out the x and the top and bottom.
Yep. So in this case, we're just left with 1 over x plus 10 e to the x dx, right? So, which in this case is a lot simpler to find the antiderivative of, okay? So, using the antiderivative rules that we have, what do we get for our antiderivative here?
ln to the absolute value of x
Yep.
plus 10 e to the x.
Yep. Natural log of the absolute value of x plus 10 e to the x
Plus 2.
plus c. Good. Okay? So this will get you your general solution y of x. Okay? So that's all fine and dandy, but again, now we got to figure out what c is, right? So now here's where our additional data point comes into play. So in this case, we say, all right, well, if we let x equal 1 here, we have y of 1 equals natural log of the absolute value of 1 plus 10 times e, because in this case, e to the first is just e, and then plus c, and then by our given IVP, this is all equal to 12. Okay? So if that's the case, we say, all right, well, in this case, what would the value of this expression be?
0.
Yeah, just 0, right? Because this is just natural log of 1, which is just a big fat 0. So in this case, that should pretty quickly tell you that your value c has to be 12 minus 10 times e. Okay? So as a result of this, your particular solution, y of x, becomes natural log of the absolute value of x plus 10 times e to the x plus, well, in this case, 12 minus 10 times e. Okay? So, just as a quick definition review, this is the general solution with just plus c, general solution, and this with the actual constant given to us is the particular solution. Particular solution. Okay? Okay. So that's that problem. So any questions on that before we move on? Okay. So here's what we'll do for our next point of discussion. So the next one we wanted to talk about was limits at infinity. Okay? So here's one that could be another good topic to review. So let's go ahead and look at that. So here's some useful limits that could be helpful for the exam. So useful limits to remember. Okay. So in this case, we say, all right, well, if you recall, if we have the limits as x goes to infinity, or plus or minus infinity, in this case of 1 over x to any power n, so 1 over n where n is greater than 0, then what should that tell us about the value of this limit here? So let's consider the case n equals 1, for instance. So if we have a limit as x goes to infinity, or plus or minus infinity, of 1 over x, well, remember, if x gets really, really big, that's assuming that this gets really, really small, right? So what should that tell you about the limit of 1 over x as x goes to plus or minus infinity?
Goes to 0.
Goes to 0, right? So using similar reasoning should tell you that this limit here is equal to what? Yeah, it's also 0, right? Okay. So that's the first one. So then the limit, the next one I want to focus on is the limit as x goes to plus or minus infinity of, let's see, in this case, x to the n. So here's where we have to be a bit more careful, because in this case, usually n will be some integer. So n is an integer in this case. So in this case, we have, all right, so let's see we have n even, just to start off. N even. So the limit as x goes to plus or minus infinity of x to the n. So what would that be? So taking a look at a particular case, let's look at n equals 2. So limit as x goes to plus or minus infinity of x squared. So if we take x to be a really, really large positive number, then what should that equal? Then what should this limit be? Yeah, infinity, right? And then what about negative infinity? Would there be any difference? Nope. So that should tell you that the limit as x goes to plus or minus infinity of x squared is positive infinity. So by similar reasoning, that should tell you that this limit here, if n is even, should also be infinity, right? Okay. Meanwhile, if n is odd, say, n equals, just taking a nice case, 1, for instance. So what that should tell you is that in this case, if x goes to, say, positive infinity of x to the n, well, as before, well, that just means x becomes a really, really large positive number. So by similar reasoning, we have positive infinity. But what happens if we let x go to negative infinity? And we have n odd here. What do you think is going to happen? Goes to negative infinity, right? So again, if you consider at the n equals 1 case, if you have x goes to negative infinity of x, well, that just means x becomes a really, really large negative number, so you have negative infinity here. Okay? So this is for n odd. This is for n even. Okay? Alright. Okay, so just a quick little review of that. So with that reasoning in mind, let's go ahead and look at a couple of examples of this. So I'm just going to sort of make up a rational function on the spot here, so let's see what happens from this. So let's see. If we take the limit as x goes to infinity of, say, x to the fifth plus, let's make it 3x to the fifth plus 5x to the squared plus 7 over negative 2 times x to the fifth minus 12. Like I said, just making up some random functions here. So here's what's happening with this. So what you could do with a problem like this is that you could set up a table, pick some really, really large positive values of x and then try and deduce a pattern. But if you remember, what we had to do was we had to focus on the terms with the largest powers. So we had to focus on the leading terms here, was the trick. So look at leading terms. Okay? Because in this case, the ones that go to infinity the fastest are the ones with the highest powers on top and bottom. Okay? So that's why in this case we should focus on 3x to the fifth on top, and then negative 2x to the fifth on bottom. So as a result, we have x goes to positive infinity of 3x to the fifth over 2x to the fifth. So in this case, that should cancel out, or at least simplify relatively nicely. So we have x to the fifth on top and bottom. So as a result, these will cancel each other out. You have x goes to infinity of 3 over 2. But here's the thing. This is just a constant, right? So if x goes to infinity, what should the limit of a constant be?
Constant.
Yeah, just the same constant, right? Oh wait, this should be negative 2. Sorry, there should be a negative here. But in this case, you have 3 over negative 2, or if you prefer, 3 halves. So, but in any case, that will be your final answer here. Okay? So, just an example of that. Does that sort of get into what you were focusing on? Okay. Alright, but then, yeah, even if they're different, it would be the same idea, but you would sort of apply these rules here to help you figure out what's going on with that. Okay? Okay, any other questions on that concept? Okay. Alright, were there any other ones that you all wanted to take a look at? Because I had some ones I would want to look at if you all were interested. Okay.
Can we review some of the questions on finding neutrality?
Concavity, yes we can. So, here's what we'll do. So, let's take a look at, okay, so concavity. Okay. So, let's just do a quick little review of this stuff. So let's I be an interval in negative infinity to positive infinity. Okay, so if you recall, f of x is concave up when the second derivative is strictly positive, and f of x is concave down when the second derivative is negative. Okay? So just a quick little review of what these look like graphically. So concave up versus concave down. So what happens is that concave up, if you recall, give you sort of like a smiley face style graph on that interval. But concave down gives you a frowny face looking thing on that interval. So concave up is smiley face, concave down is frowny face. Okay? Okay. So that's a quick little definition recollection. And then we also have f of x has an inflection point at, say, x equals x naught if concavity changes at x naught. So if you recall from the increasing decreasing stuff, we had to classify relative mins and maxes from, does it change from going from increasing to decreasing or from decreasing to increasing? But in this case, we don't have a formal definition for those the respective scenarios in changing from various concavity behaviors. So in this case, if it just goes from concave up to down or vice versa, then it's just called an inflection point. There's no fancy definitions for those specific cases. It's just an inflection point. So let's take a look at, let's see, which one do I want to do? Let's do simple ish example. So let's do example from, I'm going to do example 1 from the challenge packet because that's the first thing that I'm looking at. So we have f of x equals x to the 4th plus 4x, x to the 4th plus x cubed minus 3x squared plus 2. Okay. So in this case, if you want to find the concavity points, well, let's go ahead and take a look at the second derivative. But in order to find the second derivative, well, you should probably find the first one, right? So what will be the first derivative of this thing?
Oh, 4x cubed plus 3x squared minus 6x.
Yep, minus 6x, good. So 4x cubed plus 3x squared minus 6x. And then so the second derivative should then, as a result, be what?
12x squared plus 6x minus 6.
Yep, plus 6x minus 6. Okay. All right. So what happens from this is that, if you want to find the inflection points slash concavity intervals, well, we need to take our second derivative here and then set it equal to 0. Okay? So if we do that, well, let's see. If we take a look at this quadratic, is there any really clean way to factor this? No. So if there's not, that should probably indicate you should probably use the quadratic formula for this. So before we do that, is there anything we can factor out of each term here? 6, right? So if we factor out 6, we get 2x squared plus x minus x. So then if we apply the quadratic formula on this thing here, on the inside, oh, I should probably move this up, sorry. Then if we apply the quadratic formula, we, let's see, get x equals, so if we apply the quadratic formula on this thing here, what should we get at this?
I was going to say that it's 2x squared plus x minus 1.
So what was it?
2x squared plus x minus 1.
Oh, sorry, yeah, sorry. Yep, sorry. Okay. But yeah, so then now we apply quadratic formula on this thing, what happens? So x equals, okay, I think some of us need to have a quick recollection of that. So if you recall, the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm going to keep using that song so that way you guys can remember it. So I know it's stupid, but if it helps you remember, then please use it. Okay, so if we use that on this guy right here, we have x equals negative 1 plus or minus the square root of 1 squared minus 4 times 2 times negative 1 all over 2 times 2. Okay. So now that we have that, we say, all right, well, we have negative 1 plus or minus the square root of, well, how does this simplify? So we have essentially 1 plus 4 times 2, so that's just 9 all over 4. But thankfully, that just becomes, well, negative 1 plus or minus 3 over 4. So that should pretty quickly give you that two solutions to this are what? So yeah, one of them is 1. If you focus on negative 1 minus 3 over 4, then you focus on negative 1 plus 3 over 4, well, that should get you 1. Sorry, yeah, negative 1 and then 1 half. Okay. Okay, so your two solutions are negative 1 and positive 1 half. Okay. So those will be your potential candidates for inflection points. So let's draw a number line for the second derivative to see where the concavity changes and where we have concave up versus down. Okay? So here's our f double prime. So if we have -1 here and then 1/2 here, then I'm going to put zeros here to indicate that this is where the second derivative is 0. All right? So because of this, that should tell you, all right, so if we apply we pick various points inside each of these 3 intervals and plug them into f double prime of x, that should tell you that that should give you the signs of each of these 3 intervals for the second derivative. So if we pick something and say -infinity to -1, then plugging that into our second derivative should give you what? Should it be something positive or something negative?
Positive.
Yeah, it would be something positive, right? Because if you pick, say, -2, for instance, then that should get you something positive. But what about -1 to 1/2? So if you plug something in there, what should happen?
Negative.
Negative, right? Because if you plug in, say, 0, then that should be 0, or sorry, less than 0. And then in a similar fashion, if you have something from 1/2 to infinity, if you pick, say, x equals 1, then that should be positive. Okay? So as a result, that should tell you, all right, well, that means you have positive second derivative here. So that means you're going to have concave up. And then similarly with the interval here as well. But then because this interval gives a concave down, you're going to have negative second derivative or concave down. Okay? So in this case, we have, all right, so the concave up intervals, like I said, are going to be these 2 intervals here. So we have -infinity to -1, and then 1/2 to positive infinity. And concave down, meanwhile, is going to be -1 to 1/2. Okay? So as a result of this, we say, all right, well, it's good we have the intervals of concavity, but now let's go ahead and figure out what the inflection points are. So if we do that, we say, all right, inflection points at what 2 points? So in this case, they would be at, x equals, so if we focus on our 2 candidates for inflection points, so based off of the behavior that we established in our number line here, what should that tell you about the inflection points that are going to be given for this graph?
-1 and 1/2.
Yep, -1 and 1/2, good, because those are where the concavity changes, but the thing now is that sometimes the problem may ask you, just give me the x coordinates and that's it. But sometimes it may also ask you, maybe just find the actual point on the xy plane where we have an inflection point. So they may also ask you, tell me where on the xy plane we have an inflection point, as opposed to just the x coordinate itself. So in this case, if we have, say, -1, we have this point here, then do you guys remember what the corresponding y coordinate should be? Do you guys remember how we get that?
Put it into your original equation.
Yep, we got to plug it into the original function, right? So we got to plug it back into the original function here. So in this case, you should have f of -1. So if you plug in -1 into the original function, well, let's see. What should you end up with here? Right. -3, okay. And then what about if you plug in 1/2 into the original function? What happens with this? You can use a calculator if you need to. Go ahead.
23 over 16.
Okay, 23 over 16. All right. Okay, so those would be your 2 inflection points on the xy plane. So, like I said, if you just need the x coordinates, then this would be your answer. But if you actually need the 2 points on the xy plane, then this would be your final answer for the inflection points. Okay, so any other questions on any of that? Okay. So, let's see. So, I think what we'll do, does anyone have any other things they want to look at? Because I have a couple others that I think would be interesting ones to look at, / review. Okay, so why don't we take a look at the ones I might look at for the... Here we are. Let's take a look at some graphs of derivatives. So, basically I'm focusing on lesson 21 here. So if we have graphical interpretations of derivatives. So remember, with these types of problems, you have to make sure you know what you're focusing on here. So in this case, you have to be given a graph of the derivative. So a common mistake that a lot of students make is that they just seem to think, oh, here's a graph of some function. Well, you have to be careful. You have to focus on if you're given the graph of a function or you're given the graph of the derivative of the function. So you need to make sure to keep that in mind. So in this case, what you might be asked is, something involving, any combination of these 8 concepts here. So, critical numbers, increasing, decreasing intervals, the relative min and max, concave up and down intervals, and inflection points. So just keep that in mind for these types of problems. So in this case, if we go ahead and take a look at this particular graph from the challenge problem packet, let's go ahead and find each of these 8 concepts. Again, I'm not sure if you'll be focusing on something like this, like focusing on all 8 of these for a question problem, but you never know. So just covering all our bases here. So we'll focus on the critical numbers first. So in this case, we have to focus on critical numbers are x values where the derivative is equal to 0, or where the graph touches the x-axis. So what I'm going to do is I'm actually going to extend this a little bit and say, okay, this is supposed to be 11. So taking that into account, let's go ahead and find the x values at which there is a critical. So this is the graph of a derivative of a function. What should this tell you about the critical numbers of f of x? So if we take a look at the graph, we say, all right, well, where's f prime of x equal to 0? So this is the graph of f prime of x. So you have to focus on where the graph touches the x-axis. So taking that into account, what would our x values be that we need here? So let me try to zoom in on this. Okay.
1 through 7, 9, 11. Would 5 also be included?
Yep.
Okay.
Because in this case, that does include that does touch the x-axis, so that does count. 7, 9, and 11. Okay. So the next thing we focus on is increasing intervals. So in this case, if you recall, the increasing intervals corresponds to when f prime of x is positive. So in the context of our graph, we have to focus on where the graph of our derivative is above the x-axis. So taking that into account, we should have what intervals for our increasing intervals. So what? Oh yeah, sorry. What was it?
Negative infinity to 1.
Negative infinity to 1, sure.
3 to 7.
3 to 7, right? Because remember, in this case, if we're going from increasing to increasing again, that means that you have to include the point that's not included in these 2 intervals. So you have to include x equals 5 here. Okay, go ahead and continue.
And then 9 to 11.
Yep, 9, 11. Good. Okay. So let me just make a quick little remark here again. So again, in this case, you would normally have, technically 3 to 5 and then 5 to 7. But in this case, since these 2 intervals are only missing 1 point that is inside the domain of the function, x equals 5 in domain, So compress to 3 to 7. Okay. Yep.
How would you know to put negative infinity since the graph doesn't go past 0?
So in this case, if you're not given any information about the graph, you can say, all right, well, you can assume this sort of stretches off to negative infinity. But if the problem says, focus on, the graph of the derivative with domain explicitly equal to this, for instance, 0 to infinity, then you can interpret it that way. But here you can assume, unless explicitly otherwise stated, you can assume that it stretches off to negative infinity, to positive infinity. Okay. Yeah, so I'll go ahead and put that here to clarify that. But in this case, if you say put this as 0 instead of 1 on the John's prompt packet, I will not say that's wrong because of the way the graph is drawn on the packet. But, okay, but moving on. So decreasing intervals. So in a similar fashion, if you're focusing on when the graph of the derivative is positive for increasing, similarly that should tell you that decreasing means you got to focus on when the derivative is negative. So with that reasoning in mind, what should the decreasing intervals of our function be, using the similar reasoning from this?
One to three, and then 7 to 9, and then 11 to 12.
Yep. 7 to 9. So yeah, 1 to 3, 7 to 9, and 11 to infinity. Okay, so the good news is that takes care of our increasing and decreasing intervals. So now the next thing we have to focus on is the relative mins and maxes here. So relative min and relative max. So in this case, you're not given any information about the graph of f of x. You're not given any information on that. You don't have any data points you're given, so the best you can do is say, I just need the x values here. So in this case, if we were to draw a number line corresponding to our graph here, so we have, all right, as we mentioned, we have critical numbers at 1, 3, 5, 7, 9, and 11. So let's go ahead and draw those. So we have 1, 3, 5, 7, 9, and 11. Okay? So using our increasing and decreasing intervals that we've established in above, then we have increasing is negative infinity to 1. So northeast arrow pointing this way. And then from 3 to 7, we also have increasing. So increasing for these northeast pointing arrow for these two. And then 9 to 11, we have increasing here. And then for decreasing, we have 1 to 3. So southeast pointing arrow. 7 to 9. And then 11 to infinity. Okay? So with that reasoning in mind, that should tell you, all right, well, what would the relative min, where would we have, what x values where we have a relative minimum? So if you call relative minimum means we're going from decreasing to increasing.
3 and 9.
Yep, 3 and 9, good. And then relative maximum similarly means you went from increasing to decreasing.
1, 7, and 11.
Yep, equals 1, 7, and 11. Okay. So yeah, in this case, I do have formal definitions for the relative extrema here, but if you don't quite remember these, you can always just say, all right, well, if I don't remember these, just draw a number line, and that will give me the answer pretty quickly if I remember the concepts from the last exam. Okay. So that gives you critical numbers, increasing, decreasing, and our relative extrema. So okay, that's taken care of. What about the concavity stuff that we established? So concavity, so if we focus on up and down intervals, so in this case, if you recall, these occur when the second derivative is positive, right? But that's the same thing if you recall from lesson 19. That's the same thing as saying that's when the first derivative is increasing. So, because in this case, if you focus on this, if the first derivative is increasing, that means taking the derivative of that means that you should have something positive out of this. Okay? So, using this reasoning, we say, all right, if we take a look at this graph and focus on when we have the function is increasing, that is, the function is, if you keep going to the right, if x is going along the right, that means the graph should be going upwards on that interval. That means, all right, one such interval I can think of is going from 2 to 4, because if x is traveling along the right, that means the graph is going upwards. So that's one such interval that gives concavity upwards. But using this reasoning, what's another interval I can see that does this?
5 to 6.
Yep, 5 to 6. Do I see any others? Let's give someone else a chance.
8 to 10.
Yep, 8 to 10. Good. Alright, and then concavity down is similar, except instead of focusing on when the function is increasing, concave down means you focus on when it's decreasing. So concave down says, all right, if we start from negative infinity, then what would our first concave down interval be? Yep. So, okay, so what would our first concave down interval be?
8 infinity 0, 2.
Yep, negative infinity to 2. And then someone else, what would the next one be?
4 to 5.
4 to 5. And next one?
16.
6 to 8. And then last one? 10 to infinity. Good. Ah. Okay, so that takes care of the concavity intervals. So now the last thing we have to focus on is where the concavity changes, namely the inflection points. Okay. Inflection points. Yes, there we go. Okay. So that says, all right, for inflection points, well, where does our concavity change? So taking a look at our concavity intervals that we've established, at what x values does the concavity change? Let's give some besides you two a chance. You guys seem pretty eager to answer these questions, so go ahead.
2, 4, 5, 6, 8, and 10.
Yep, 2. So changes at 2, 4, 5, 6, 8, and 10. Okay. Because with x equals 2, for instance, it goes from concave down to concave up. And then, for instance, with x equals 4, it goes from concave up to concave down. And then so on and so forth. Okay. So any questions on that problem? Okay. So I'm going to do one more problem. Let's see. I'll make, since we've only got about 5 minutes left, I'm just going to make it relatively quick. So what I'll just do is say, all right, let's focus on a somewhat challenging antiderivative problem. So find y of x if y prime of x equals 2 over the cube root of x to the 4th minus the 4th root of x to the 3rd over 2. So again, it seems like we have another problem that looks like there's a bunch of similar terms that might throw you off. But in this case, just with problems like this, it's just better to just take a step back, look at each individual term and see how I can simplify it using the derivative rules I know, and then work from that. So, and that reasoning in mind, let's take a look at this first term here. So we have 2 on the top, so this is going to be 2 times something. So with this x on the bottom here, that should mean, all right, we should be able to rewrite this as 2 times x to the some power. So given that get x is on the denominator, and the denominator is the cube root of x to the 4th, what do you think that power is going to be up here? So maybe let's take another step back. So if we focus on the denominator here, just focusing solely on the denominator, this is the same thing as saying 2 divided by x to the what power? So just focusing on just this thing right here. So we have the cube root of x to the 4th. That's the same thing as saying x to the what power?
4/3.
Yeah, 4/3, right? So with this reasoning in mind, that should tell you that this power here should be what? Negative 4/3, good. Okay, and then doing a similar thing with the second term, says that we have 1/2 times x to the what power? Go ahead. 3/4, good. Okay, so like I said, at first this looks pretty daunting, but once you actually take a step back and use algebraic / exponential properties, then it actually becomes a lot easier to work with. Because now, we know how to take the antiderivative of each of these two things. So y of x is equal to the antiderivative of 2 times x to the negative 4/3 minus 1/2 times x to the 3/4 dx. Okay? So using this, we say, all right, well, how do we take the antiderivative of this? So if you recall, we have that the antiderivative power rule says that, I'll just put it here, so x to the n dx, that's equal to x to the n plus 1 over n plus 1 plus c. Okay? For n not equal to negative 1. Okay? So that's the antiderivative power rule. So that says, all right, if we apply this antiderivative power rule to each of these two terms here, then what do we end up with as our general antiderivative of this thing here? So first off, we have applying power rule on this term here will give us what?
Is it x to the negative 7/3 or
Remember, you're adding plus 1 to that, not subtracting.
should be negative 1/3?
Negative 1/3, right? Yep, good. Okay. And then minus 1/2 times x to the what power? So in this case, we,
3/2.
what's that?
Is it 3/2?
You remember, you're adding 1 to 3/4.
7/4.
7/4, good. Okay. And then, of course, your plus c. Okay. So with that reasoning in mind, let's go ahead and simplify this a bit more. So we have, all right, we have, 2. So in this case, if we focus on this coefficient here, that means we're going to have 2 divided by negative 1/3. So how does this simplify? So in this case, we're dividing by a fraction. So that should give us what?
Negative 6.
-6. Good. Because remember, dividing by a fraction is the same thing as multiplying by the reciprocal. So we have 2 times negative 3 over 1, which is just negative 6. So negative 6 times x to the negative 1/3. And then we do a similar thing with this term here to get what as our coefficient?
2/7.
2/7. Okay. And then times x to the 7/4 plus c. Okay? Okay. So, like I said, this is a bit more of a challenging antiderivative problem, but I figured it's good to have these just so you kind of know them for the exam, just in case, you do get asked a tougher question like this. Okay? So any questions on any of that? Okay, well, so that's the exam 3 review for the 8:30 section. So you guys can ask me any questions via email or Zoom tonight. I will have office hours from, let's do 5 to 7. So office hours from 5 to 7 tonight. I'll be on Piazza from 4 to 5, so you have plenty of time to ask me questions. But other than that, make sure to do the extra credit review by tomorrow morning if you want to do it. Otherwise, good luck on the exam, and I'll see you on Friday. Yep, see you.